So let's look at the next concept, and the next concept we have here is called the net change theorem. So it says the fundamental theorem of calculus states that f is continuous on the closed interval ab and capital F, the parent function, is the antiderivative of lowercase f. Then you can evaluate the definite integral by finding the parent function, finding the antiderivative, plugging in b, and then plugging in a. It says because the derivative of the parent function is the little function, this statement can be rewritten as the integral from a to b of the derivative of the function is f of b minus f of a. So what have they done here? All they did was swap in the little function with the derivative of the parent function. And we know those two things are exactly the same. It says when the quantity f of b minus f of a represents the net change of f of x on the interval a to b. So if f prime of x, capital F prime of x, is the rate of change of the quantity of capital F of x, then the definite integral of f prime of x from a to b gives the total change or net change of, so there's the net change of capital F of x on the interval a to b. So what do you do to find the net change? Well, let's look at an example. It says a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is the time in minutes and 0 is less than or equal to t less than or equal to 60. Find the amount of chemical that flows into the tank during the first 20 minutes. So it wants the net change from 0 to 20 minutes. So how are we going to find the net change from 0 to 20 minutes? Well, if you read, it says this is the rate that it's flowing. So this is the rate of change. So this right here represents the derivative of the amount of chemicals, right? The derivative of the amount of chemicals. So how are we going to do this? We're just going to set it up, the integral from 0 to 20 of the change in chemicals, which was the 180 plus 3t. Of course, this is with respect to t. So there's how we set it up. We just do the integral from 0 to 20 of that function because that is the rate of change. So we're integrating the derivative is what we're saying. Okay. What's the integral of 180? Well, that would be 180t in this case, plus 3 times the integral of t, which would be t squared over 2. And then again, this has to be evaluated from 0 to 20. So when we do that, we plug in the upper limit first. So that would be 180 times 20 plus 3 times 20 squared over 2. That's what happens when we plug in the number 20 minus, now we need to plug in the number 0. I'm not going to lie, I love plugging in the number 0. Why do I love plugging in the number 0? Because when you integrate something, you always have a variable. And when you plug in the number 0, it's always the number 0. So this entire thing turned into a 0. And then when I plugged in the first one right there, plug in 180 times 20 plus 3 times 20 squared over 2, I'm getting a total of 4,200. So find the amount of chemical that flows into the tank during the first. Well, look at our units, 4,200 watt, that would be 4,200 liters. So 4,200 liters of that fluid came in the first 20 minutes. All right? It says another way to illustrate the net change theorem is to examine the velocity of a particle moving along a straight line. So this is, once again, drop a ball off the roof. It's moving in a straight line down, right? Where s of t is the position function time, then the velocity v of t is the derivative of the position function. So we know that. So what do you want to know? If you want to know, it's called the displacement. It says the definite integral here in the net change in position. So how far has the particle changed in position? That is called displacement. Displacement is just the change in the position. Displacement is just the change in the position, okay?